Welcome to Understanding Wildfire with Professor Monks. Today's topic, How Fire Burns, Part 2. We've seen how fire burns at the chemical level, the processes that apply even to tiny fires like a birthday candle. But for this series, we're most interested in fires that burn at the landscape scale. Additional considerations come in when we look at these larger fires. Every fire starts with an ignition. By far the most common natural ignition source is lightning. A lightning bolt is an electrical charge that can reach up to 20,000 degrees Celsius, providing plenty of initial energy to get a fire going. Much more rarely, a fire can be started by sparks from a rock falling off a cliff, lava, or the heat of a meteor impact. Ignitions from human activity, what we call anthropogenic ignitions, are much more varied. It could be a cigarette butt, or sparks from a vehicle, or a campfire that wasn't properly put out, or electric transmission lines like the ones that started several of the major recent fires in California. And that's not even getting into the fires that people start deliberately, for reasons ranging from clearing land to hazard reduction to insurance fraud. For simplicity's sake, we can imagine the ignition happening at a single point. From there, the fire will burn outward. All else being equal, the fire will try to grow in a circle. The speed with which the fire moves outward is known as the rate of spread. It's very important to note that as the fire grows, it's really only the outer rim that's actively burning. You get an area maybe a few meters wide that is producing flames and consuming fuel. We call that the firefront. Behind the firefront is a burned out area, where all the fuel has been burned already. Animals like kangaroos know this, and so rather than trying to outrun a fire, they may simply run into the fire, aiming to quickly reach the burned out area where they'll be safe. As a fire approaches, it puts out a lot of energy. That energy dries out and heats up the fuel ahead of the fire, getting ready to burn. If we measure the amount of energy at the firefront, that's known as the fire line intensity. If you measure from the base of a flame, where it comes out of the fuel, up to the tip where it stops glowing, that's the flame length. When the flames are tilted relative to the ground, which can happen when there's wind to push the flames over, we can also measure from the tip of the flames vertically down to the ground. This is the flame height. The angle between the flames and a vertical line is the flame angle. And the horizontal width of the area that's burning is the flame depth. The flame depth is the same as the width of the firefront as our fire spreads outward from the ignition point. A fire spreads in a circle if all else is equal, but usually all else is not equal. If there's some factor that's making the fire spread faster in one direction than another, increasing or decreasing the rate of spread for one part of the firefront will turn into an ellipse, stretched out in one direction and compressed in the opposite direction. When a fire takes on an asymmetrical shape like this, we have names for the different parts of the firefront. The area that's spreading fastest is the head. The slowest area is the back. And the sides are referred to as the flanks. The most dangerous place to be when a fire is approaching is near the head. The rate of spread at the head of a wildfire can easily reach 11 kilometers an hour in forested land, or 22 kilometers an hour in grassland, overtaking a running person or even a vehicle. To see what factors will influence where the head of a fire goes when it's burning through a landscape, we can turn to another fire triangle. This one is called the fire environment triangle, and it summarizes the three most important factors that influence how fires burn at the landscape scale. First is fuel. Fuel was part of the regular fire triangle because all fires need fuel to burn. At the landscape scale, the composition and arrangement of fuel influence how a fire moves. Obviously, if there's no fuel somewhere, the fire will stop completely when it hits that spot. If there's less fuel, or the fuel is harder to burn, perhaps because it's wet, or because it's made up of big chunks like logs rather than smaller branches, the fire will slow down, and the fire line intensity will drop. On the other hand, if there's lots of fuel, arranged so that it can easily get oxygen, then the fire will burn quickly and intensely. Some plants, like the eucalyptus tree, are full of oils that make great fuel, so fires burn especially hot and move especially fast through eucalyptus forests. An important concept to keep in mind about fuel is that not all fuel that exists in a place is necessarily able to burn in a given fire. For example, a piece of wet wood might not burn if the fire line intensity is low, but a more intense fire would be able to burn it. Similarly, a very thick log or tree trunk won't burn in a low intensity fire, but can burn in a higher intensity one. We say that only some fuel is available to a certain fire. Fuel that is present but not available might still burn later if another hotter fire comes through. The second leg of the fire environment triangle is topography. Topography means the shape of the land surface, the arrangement of hills, valleys, plains, etc. In brief, fire is the opposite of water. It moves faster uphill than it does downhill. To see why, consider some fires on different slopes with the same flame length and the same flame angle. The fire has to heat the fuel ahead of it in order to ignite it. The closer the fuel is, the hotter things are, and the quicker the fuel will catch fire. Fuel that is upslope from the flames is essentially tilted toward the fire. The distance from the fire to the fuel ahead of it is less, whereas the opposite is true for fuel located downslope. It's farther away and thus harder to heat up. This means that fires can race up a hill, then slowly mosey down the slope on the other side. Houses and buildings located on top of hills are at high risk when fires start in the valleys below. And the third leg of the fire environment triangle is weather. Weather conditions can drastically impact how a fire progresses. Generally speaking, cool and wet conditions reduce fire line intensity, hot and dry conditions increase it. Fires that are deliberately lit for hazard reduction or ecological benefits, for example, are usually done in cool, wet conditions so that they're easy to control, but not too cool and wet or else they won't burn at all. In many cases, firefighters have to wait for a shift to cooler and wetter weather before they can try to attack and contain the head of a major wildfire. Wind plays a major role in shaping how a fire spreads. Fires will spread more quickly in the direction the wind is blowing, and more slowly when they're spreading against the wind. And this is for basically the same reason that fires spread quickly uphill and slowly downhill. The wind tilts the flames, bringing them closer to the fuel ahead in one direction and farther from the fuel in the other direction. When there's a steady wind blowing, a fire will take on an elongated ellipse shape with a relatively small head. But watch out. If the wind shifts direction by 90 degrees, suddenly that long flank becomes the new head. A change in direction like this was one of the things that made the Black Saturday bushfires in Australia in 2009 so deadly. The wind had been blowing out of the west, creating a narrow head spreading eastward. But then the wind swung around to come out of the north, and the long southern flank became the new head, advancing rapidly on homes and people. Wind also contributes to another important form of fire spread. A bit of burning fuel, like a leaf or a branch, can get blown out ahead of the fire front, igniting a new fire. This phenomenon is known as spotting. Spotting makes firefighting tricky because it can enable a fire to jump across barriers like roads and streams and areas with no fuel that have been cleared in order to try to stop the fire. How far ahead spot fires will occur depends on the strength of the wind as well as the aerodynamic properties of the pieces of fuel. In some cases, spot fires have occurred several kilometers ahead of the fire front. With a topographic map and some weather data, you can work out by hand how a fire is likely to spread. But today, we have sophisticated models that use geographic information systems to calculate exactly how a fire would respond to a given set of conditions. Fire managers use these to plan how to deploy firefighting resources, where to order evacuations, and other critical decisions.